Okay, great. All right, everybody. After some amazing technical setup from our student volunteers, we now have a working presentation. Um, uh, Kobe, take it away. Tell us about how to formalize binders.
Okay. Thank you very much, and my apologies to you all for the miscommunication, and thanks for the quick setup. Yeah. So I'm going to talk about joint work with Benedikt Ahrens and Ralph Matthes about the use of monoidal categories in order to study and formalize syntax with binders. So the motto of the talk is the following, and that formalizing a given piece of mathematics, it's not obvious, but sometimes it becomes simpler by generalizing the mathematics. I assume that most of you already know the first sentence, and that all of issues can appear. But I hope to convey you that by generalizing mathematics, we can sometimes overcome some of these issues. And so I'll first tell you a little bit about just the background of the project that we worked on and where we actually noticed this. And this was in the study of simply typed languages. And then I'm going to show you two abstraction layers that we can use. So yeah, just about our setting. So we worked in a specific Coq library called UniMath, a library of univalent mathematics, which just uses Coq files, but no specific plugins. However, the problems that we have encountered, it's not HOTS related, but it's more generally to any intentional type theory. So the area where we had these kind of issues was in the study of the simply typed lambda calculus, or more generally in the study of programming languages. And so the mathematics in particular that we need to formalize, well, it started off with a signature, or with a notion of signature, which specifies the domain-specific part of the constructors. And so this is usually a collection of n-valued lists. So for example, for the n-type lambda calculus, we have two domain-specific constructors, which is the abstraction and the application. The variables is something which is actually already part of the framework, so that's why we do not need to include it. And then this function, in this case, it just maps, well, the abstraction constructor to just a list of one element with value 1, because there is one bound variable. And then in the application, there are two input arguments but no bound variables. And then having a notion of signature, and we want to study its models. And in our case, it's in terms of monads. Well, in order to get this, we need some kind of signature functor, which then, if we have constructed such a signature functor, that we then get a initial algebra, which then represents the type of untyped lambda terms. And this is, well, and as you can see here, the output of this functor, it has here an X composition with option. We just add just a singleton to the input. And this is precisely in order to get the abstraction. Now for the application, we just need two variables. Yeah, and then in order to, for example, get to these models, we also need some intermediate structure. So this is also something that that we have to formalize, and then in the end, the end goal is to get some kind of initial semantics. So this is, for example, the inductive data type that you would expect for the untyped lambda calculus. And this is actually something that you then can receive by first defining a signature, then getting then defining this functor h. And then if you take the initial algebra, we get this. And then on top of it, you also want to have some kind of monad structure in order to get the notion of parallel substitution. Now, when trying to formalize this, or even especially when going to the simply typed case, we encountered some problems. Well, of course, as everyone already always has, that there are very nasty technical details. But more specific to our case is actually that we have very excessive unfoldings. And it's actually because we work with a very particular mathematical structure. And so Coq actually already knows, a lot more details that we actually want to abstract away from. In particular, we also have some type checking issues. And this actually becomes when trying to apply the simplification tactics. And that these goals don't type check is because under the hood there are automatic conversions going on. And so in order to overcome this, one has to add certain parameters also explicitly. But this is in general very annoying to have to deal with these kind of things. And so the solution that we have used is to actually use more abstract mathematics. And in the rest of this talk, I will give you actually two examples where we've used some higher abstract mathematics. Okay, so now let me first say a little bit about the study of simply typed languages, or it's semantics. So it's the same as in the beginning for the untyped. We first, we need a notion of a signature. And this can be represented by a multi-sorted binding signature. And so again, we have here two constructors for the application and the abstraction. But now the signature looks a little bit more complicated because we also have to add the different sorts. Then we want some kind of categorical syntax specification, which we then call a semantic signature, or a signature with strength, to be more precise. So I'll say something more about this in the next slide. So this is some kind of intermediate step. So in order to understand the syntax a little bit better, and then in order then to come to a semantics, and then now the inductive data type, which specifies the simply typed lambda terms, is then of this form. And so this semantic signature, what it does, semantic signature consists of two parts. The first is this is a so-called signature functor, and for this, we consider just a set of sorts, or the types that we want to include in our language, and then any function from this set of sorts to sets or to types can then be thought of as a sort variable supply. So to each sort we associate a set of variables, and this gives in the untyped for the untyped lambda calculus, we just had a functor just from, let's say, from the functor category or the inner functor category from types or sets to sets. But now we also have to include our set of sorts. And here you already see here we worked with an abstract category C. But in the end, we will always instantiate it to a category to the category of sets or the category of types. And so this signature functor, this specifies in a way all the constructors, but we want to have eventually the minimal kind of functor actually that we want to represent. And so we have this general functor, but then we want to take the initial algebra of it. And so to be a little bit more precise about this, and so we have here this functor, and this specifies the language, or it's supposed to be. And what we then do is, we first have to add the we constantly have to add the identity functor. This is in order to get the variable case. And then we consider its initial algebra. And this initial algebra, this is now a functor from set to the s to set to the s. And if we then evaluate this in a functor, then we get the terms with respect to this to this sort of variable supply, and then if we apply it to a specific sort S, we get precisely the terms of that sort. And then in the end, we want to have a monad structure on this T in order to represent the parallel or the monadic substitution. And so that was only one part of the semantic signature. And so we have here our functor h, and but then in general, such a functor h of that certain type, it does not have a monad structure. And so we need to ensure that it does have the monad structure and the loss. And well, for this, there is this intermission notion of strength. Well, the precise details of that do not matter, but this is well, a natural transformation between functors of the following type, where PTD is the category of pointed Indo functors on CS, and then again has some laws that depend on the monoidal structure of this category of pointed Indo functors. Even though this, let's say, some quite technical details, the important part here is actually that you saw here that a lot of functor categories pop up, or always these kind of Indo functors, and this is actually what leads us to a first abstraction. And the issue actually with these functor categories has to do with composition. So, so to recall, if we have a functor from C to D and a functor from D to E, we get a new functor f dot g, and it goes from C to E. So here we use a diagrammatic order. Now, one of the things that, let's say, maybe you would expect is that if you compose f with the identity functor, you get f back. But this is actually not convertible, and the reason, or this has to do actually with the functor loss. They might not be they're not definitionally equal, even though they form a proposition. But on the other hand, what you do have is that the type of natural transformations, for example, say the natural transformation which start in f, that this is convertible with the type of natural transformations which start with f composed with the identity. And this actually has to do just because natural transformations, they do not depend on the loss of the functor. And so, so if you actually combine these, or actually from two, it then follows that we are able to compose natural transformations, where on the one hand, here in alpha, the codomain is just f, while with the second natural transformation, the first is the identity composed with f. Because then this composition is well defined, and precisely because this type of natural transformations are convertible. And also, if you have some kind of functor which acts on functor categories, and then this is also well defined. However, if you actually apply this functor h to both alpha and to beta, and if you then compose their output, it is actually no longer well defined. I guess the goal, it doesn't type check anymore. And well, this there is, one can work actually around this issue by just always, if you have, for example, such a nice transformation from A, where you have h of alpha and h of beta, you can intermediately put something which is then polymorphic function, which actually pointwise the identity. Now, of course, this is something that you have to do always manually, but if one works with monoidal categories, then this is actually something that always happens. Monoidal categories, they justify actually this workaround, what happens here. And moreover, they also tell you explicitly where those functions, which are the identity, have to be placed in order for for certain goals to type check. So let me quickly recall maybe what is a monoidal category, or I'm going to give you a partial definition. So a category, it's something with a monoid structure. So you have a multiplication, both on the objects and on the morphisms. This is usually called a tensor. And then we also have a unit object.
5 minutes left in the session, and I don't want to eat into the break too much. And I see that you have 10 slides left. So I just want to make sure that you cover the most important parts.
Oh, okay. Thanks. Okay. Yeah. So the points of of this slide, let's say, is that actually if one works with an unspecified or an abstract monoidal category, if you tensor with the unit object, you don't get equality on the noise with the object that you started with. In the case here, we are interested in endofunctors, functor categories, and even though if you would work really in an endofunctor category composing with the identity, the natural transformations are convertible, but in generally, but really as functors not. But if you work in monoidal categories, you no longer have this, let's say, this weird phenomena, because this, what they call the uniter, will always, needs to be there. And so if you work with monoidal categories, you no longer have hidden polymorphic functions. In particular, also the goals or sub-goals always type check, and also certain unfoldings no longer happen, and because it won't, for example, fold out the definition of functor composition. You just consider it something abstractly, and also the goals or the proof goals are much more clear. But this is not always sufficient. Actually, if one wants to consider, for example, if one wants to, for example, study the signature functor, the monoidal category, let's say the monoidal categories can be used precisely because we're always functors, or we work here with functor categories whose domain and codomain are the same, but the building blocks don't longer have the same codomain. And so we need to find something more abstractly, and this is where bicategories come in. The precise definition of it doesn't matter, but what you actually have is that now your home sets or your home types, they also have a category structure, and the primary or a primary example of that is the bicategory of categories, where because then if you work with abstract bicategories, you can just work with this home categories. And there's also then a way to, in order to not use actually functor categories explicitly. And so maybe then to wrap up, I'm going to show you some maybe examples. Here we have not used this abstract setting of bicategories, but if we do here as a CBN command, see the goal, it's unprocessable. Say you really can't work with it, you really have to make a big effort in order to read this. But if you would write this out on paper, actually the goal now just looks something like this, which is actually much more easy to work with. Now, here, this marked area, here you can actually see in order to get to this goal, you have to do a lot of stuff. And we have to put all the difficulty is now being actually put in the context, and even the context is not really that reason. That's readable. I mean, you have to here. You have to change the goals. You even have to match your goal so that certain things type check. And so here, actually, this proof here, we actually couldn't use this CBN tactic. Well, just because, well, then we get something of this form. Now, on the other hand, here, if when, for example, use the in this by categories, so this is actually the same lemma that I showed before, but in the more abstract setting, we can see that we actually used here CBNs and simplification, and actually the goals stay very reasonable or readable. And here is another example of that, but that is not even something that we have proved without the by categories, because it's it's such a trouble to try to do it in the very concrete case. So, as a conclusion, let me recall the motto that I said in the beginning, that formalizing a given piece of mathematics, it's not obvious, but sometimes it becomes simpler by generalizing the mathematics. Thank you very much. Are there any questions? I hope I didn't go over the 5 minutes.
Yeah, we maybe have time for one question before the break.
Mm-hmm.
Hello, I'm Ambroise Lafont from the University of Cambridge. You had you were on a slide with you were mentioning categories. I just wonder what you were about to say, because I think it was on the slide where you had to hurry up.
Mm-hmm.
So.
Oh yeah, there's actually what I was planning on saying about that is that actually also abstracting the, or how to say it, actually this signature functor is of a very specific kind, and actually what you just need is the structure of categories. And so actually, then, I mean, instead of considering just monoidal categories, you can also just work then with categories and use the theory developed for that.
Okay, thanks. And so categories were not enough to get a proper abstraction of the proof.
Well, in the examples here that I showed, it's indeed more easy to go to the by categories, but the categories, they also present you with another point of view.
Okay, let's thank the speaker again.